Yeah, our 2 days before or after prom weren't enough, and the holiday Monday, we got still lots of people away today. But yeah, so we're picking up from yesterday where we learned that A gives you the y-intercept, B tells you how the graph increases or decreases, and we're looking at the effect of dividing by 2 in this exponent. So I'm going to play catch up with the people in class. So minus 2, 8. Minus 2, 8. Minus 1, about 5.6 or so. 0, 4. Excuse me. 1, 2.83, around there. 2, 2. 3, about 1.5-ish. And then 4, 1 I can fit on there. All right, so it still looks like an exponential that's decreasing, swooping down. Looks like we're approaching our asymptote of y equals 0 still. Let me graph this in here. Still decreasing like that. And I'm going to improvise. So don't improvise when you guys start teaching your math classes. I'm going to add in another graph here. For comparison, can you guys use either a different color or like a dashed line? But I'm also going to graph 4 times 0.5 to the power of x over 2. Let's graph it, then we'll label in a second. So, guys, all I'm doing here is I'm going to just graph what the original would look like if we didn't have the divided by 2. So we've already probably graphed this one yesterday. Normally, we would start at 4, and then every unit we would have or divide by 2 or multiply by 0.5. So I'm going to start at 4 and just graph what it would look like if we were halving every unit. So then we would be at 1, 2, and 2, 1, and 3, 0.5. And then if we go back the other way, minus 1, 8. So I'm adding in a separate color here. It would look like something like this. And that second graph here is f of x equals 4 times 0.5 to the power of x. All right, so I'm going to see if you guys can complete these properties here. Here is 4 times 0.5 to the power of x. Start at 4, halve every unit. What's different about the one where we divided the x by 2? What's its y-intercept? Is it increasing or decreasing? And can you state a rule for what's happening to the y values? I'm going to wait a minute or a minute and a half for you guys to think about that, especially the rule for the y values. I might do my attendance while you guys have some think time.
Thanks.
All right, and we're back. All right, would you guys agree with this new twist? The y-intercept did not change. It was still 0, 4. So that number out front still gives you the y-intercept. This graph was still decreasing. So whether that number's bigger than 1 or between 0 and 1 still affects increasing or decreasing. But the rule is different. Did anyone see what the rule is for this graph? Forrest, you see what it is? It takes 2 units for it to decrease. Exactly. So for this one, it took 2 units to go to 4, another 2 to go to 2, and another 2 to go to 1. There is a rule for how you go to 8 to 5.66 to 4, but it's overly complicated for our purposes. This is a simpler rule. Easier, rolls off the tongue. The y values halve because of the 0.5. But yeah, so it's Forrest said every 2 units. So in my opinion, have every 2 units. We don't need to do more of those. I think you get the idea, but this is kind of where everybody kind of stops at a common ground. The 3m's will stop here. These kind of functions will be enough to model basically anything in real life. If you have a function like this, a times b to the power of x divided by a number c, our value of a still gives you the y-intercept 0a. Our value for b, the base, just to save some writing, I'm just going to say c above. It's the same as above. It tells you how the graph is increasing or decreasing. But this is new. When you divide that variable in the exponent by a number c, what this tells you is the following. It tells you, these are my own words, how long it takes to increase or decrease. So the base b will tell you doubling, tripling, halving, or whatever. This number tells you how long it takes to do that. And in our question above, that 2 meant it took 2 units to apply this rule. So that's it. That's the new thing. So let's put this into practice, and we're going to see that sketching, it's not so bad. It's basically what we did yesterday with this new twist. So now, both classes, I give you a function like this, and you guys know how to interpret all 3 numbers. So we look at the 8 out front, same as yesterday, life is good. Y-intercept 0, 8, so we know where to start, 0, 8. We look at the base, 0.5. So the y values have decreasing, and then it just depends on what you like. If you like writing times 0.5 or divided by 2, it doesn't matter to me. They're all the same thing. But the over 3 means it's going to take 3 units for our y values to have. So what will that look like? So you start at 0, 8, and then you apply your rule. In 3 units, you decrease to 4. And then in another 3 units, you decrease to 2. And in another 3 units, you decrease to 1. It kind of just stretches it out. Not so bad. We can all do this. I believe in you guys. Working backwards, we could also get 1 more point on here. If you go back 3, that would get you to 16. So in your both classes assignment a bit later on today, that's fine. I missed a point. Whatever. You guys will get more practice graphing a few of these, but really you did all the heavy lifting yesterday. Graphing these is not so different. It's just this one's every 3 units. You guys okay with that? That's not so bad, right? But yeah, this is going to allow us to model really anything that obeys exponential growth or a decrease in real life. So now we're all ready for Monday. So can you guys try this next one? So not only do you have to pick off where we start, but you guys have to pick off the rule. What's the rule for, are we doubling, are we halving, or tripling? And how long does it take to do that? You guys might have to search for some nice key points. And if you think you have a rule, like if you think this one is halving every 4 units or whatever, just test it out and make sure you land on the points your rule predicts. So while you guys do these 2, I have things to distribute. I'm going to give out the assignment for the 3Ms, and then I'm going to give out part 2 to the 3Us. So that'll just take a moment. I'll pause the recording too. That's okay. All right, people working at home, you can check your answers for these 2. In the classroom, my 3M people are now ready to go for the assignment. You can now graph any function of this type. So you're graphing a few, you are creating a few equations. It honestly should go by pretty quick. So just as a reminder, when you guys finish, make sure your pink assignment's done too. And I know for a fact that I don't think anybody has finished all of the rational exponents practice from earlier in the week. So we got lots that we could be working on. All right. The 3U people are moving into something new. All right. What I'd like you guys to do, can you guys graph 0.5 to the power of x for me? It's a bit simpler than the ones we've been just recently doing, but the rules still apply. Y is to 1 halves every 1 unit. Can you guys make a sketch of that one for me? While you guys do that, I'm going to get this second graph, 2 to the power of negative x. Ooh, interesting. I'm going to graph that one in Desmos. All right, this should be super quick for you guys. So 0.5 to the power of x, that's like 1 times 0.5 to the power of x over 1, if you want to frame it in today's stuff. So we start at 1. Every unit we're halving, which means if you go backwards, we're multiplying by 2. Level 4 for that one for me. Fine motor skills were on point. All right, did you guys get a similar graph? I wonder what the graph of 2 to the power of minus x is. This is weird, right? This is not like anything we've done. What does the graph look like? Well, here we go. I've got Desmos loaded up. Contain your excitement. Here's the graph of 0.5 to the power of x. That's in red for my colorblind people. That's red. There's the first one. Now look what happens when I graph 2 to the power of negative x. It's the same graph. It's the same graph. Interesting. They are the same graph. So on the second grid, you guys can you can write same graph if you'd like. For me, for completeness sake, I'm just going to sketch it. We got the same graph. So first key idea, hopefully you guys are convinced with that just simple exercise. Key idea number 1 for you 3 people. Key idea number 1. 2 very different equations, looking equations, can produce the same graph. All right, so that's the first key idea. Now this is true. This isn't actually really that new for you guys. You guys remember first unit reviewing quadratic functions? You had vertex form, factored form, standard form. The same parabola, quadratic function, could look very different depending on which form of the equation you looked at. It's the same with exponential functions. 2 equations that look very different can produce the same graph. Key idea number 2, I'm going to show you guys why these 2 graphs produce the same result. So this is my requirement for you 3U people. So listen up, guys. For you 3U people, I'm going to require you to actually prove why these 2 different equations give the same graph using the exponent rules you already know. So what would that look like here? I'm going to take my second function, which was 2 to the power of negative x, and we're going to show this is equivalent to 0.5 to the power of x. This one is fairly quick. We're going to use our exponent laws in reverse. I'm going to write this as 2 to the power of negative 1, all to the power of x. Right? That's just how our power of a power rule works from grade 9. Negative 1 times x, negative x. But you guys now know what you knew in grade 10. But we reviewed this. 2 to the power of negative 1, that is just 1 over 2 to the power of positive 1, i.e. 0.5. We have shown, algebraically, that these 2 graphs are the exact same in every way. The graphs are the same. We showed algebraically their equations give you the same thing. We're going to do that exercise a few more times. Let's do that exercise with this one. Now I'm going to turn this one on its head. Can you guys sketch 4 to the power of x for me? You guys sketch this one, and I'll get the next one queued up. I wonder what will happen. I wonder. So you guys sketch 4 to the power of x. And I will get that ready. All right, 4 to the power of x. So y-intercept of 1, quadrupling every 4 units. Like, I mean, practically speaking, those are the only two we can draw really accurately. But I could draw maybe negative 1.25. Yeah, it's a really steep increasing exponential function. It would go to 216, so it flies up really fast. Let's see what the graph of 2 to the power of 2x. I bet none of you guys can predict what's going to happen next. All right, you guys ready? Here I go, 2 to the power of 2x. It's the same graph. It'd be a huge rug pull, right, if it wasn't? No, it's same graph. Interesting, same graph. All right, so let's just, for completeness sake, graph those same points. It's the same graph. Same graph. Okay, but here's the exercise for us. In the space we have here, we already understand, okay, two different exponential functions can have, the equations can look very different, but they give the same graph. But why do these two give the same graph? This one is not too hard to show either. For this one, I'm gonna start with the first one. As for the y, let's start with 2 times 2 to the power of x. We're gonna use a similar strategy as above. I'm gonna be naughty here and work left to right. Don't tell Miss Flatner I'm doing this. She's in the building. She could walk in at any time. I can use my power of a power rule to just rewrite this as 2 to the power of 2 all to the power of x. That's how that rule works. Power of power, you multiply the exponents. We're just reversing that. Hey guys, and pretend you're on Barney and you just finished a song about brushing your teeth. And now we're doing 2 times 2. 2 times 2, or 2 squared, is equal to 4. We showed that these two graphs are the same graph. Just by using the rules you already know. You guys convinced? Same graph, right? Now, I'm going to just go one step further here. You guys remember from last unit, should be fresh in your mind. Period of sine x had a period of 360-degree period, right? Can one of you guys tell me what the period of sine 2x was? You guys remember the rule was the period for sine 2x. Jaden? Yeah, so how did you get 180? 360 divided by 2. This one has a 180-degree period. What happened was, we used this language last term, our graph was squished horizontally by a factor of 2. Now, if you guys look at the graph of 4 to the power of x, or 2 to the power of 2x compared with 2 to the power of x, I'm just going to flash this up in Desmos here. Look at what happens when you compare the graph of 2 to the power of x and 2 to the power of 2x. So guys, here's 2 to the power of 2x, or 2 to the power of x. With periodic functions, when you multiply the x by 2, it squished everything closer to the y-axis. Look what happens with 2 to the power of 2x. When you multiply the x by 2, everything gets squished. Everything gets squished closer to the y-axis. It's the same thing that happened with periodic functions. And in fact, the same thing happens with any function. You multiply the x by 2, things get squished, which is why we got the graph we did. Just a little extra, little tidbit, little FYI, little TIL. That means today I learned. For you guys. All right, let's do one more exercise. Let's do one more exercise. Can you guys graph this one on the left? 4 times 2 to the power of x. Yes, sir. Yeah. Put it away. It's okay. Go to the washer. Don't squish your feet. Can you guys graph that one? What's the y-intercept? What's the rule? Sketch a few points. And then I wonder what will happen with this next one. I don't know. Who can say? Who can say? All right, let's get things prepared. So we want to graph 4 times 2 to the power of x. 4 times 2 to the power of x. And then we want 2 to the power of x plus 2. Not working. X plus 2. There, that worked. All right, here I come. Can hardly wait. 4 times 2 to the power of x. We start at 4. We double every unit. So we go to 1, 8. And then working backwards, negative 1, 2, and negative 2, 1, and even negative 3.5. And we can sketch it. All right. Now, hold on to your butts. What does 2 to the power of x plus 2 look like? I wonder if it'll be the same graph. Yes, shockingly enough, it's the same graph. Very interesting. Why would we get the same graph? They're completely different bases. I'll show you why in a second. So let's, for completeness sake, just plot the other guy. Same graph, same points, and then we'll talk about the y. Same graph, shocker. But let's prove why. Let's prove why using our exponent rules. Okay, here we go. Why did this happen? Let's take the left-hand function. Let's take 4 times 2 to the power of x. In the last two, we made use of our power of a power rule. Here we do not have a power of a power. We're multiplying two things, but they're both different bases. But I'd really love if I could use my exponent rule for multiplying two powers together. Yes. You can't multiply powers that aren't the same base. Anyone have any ideas so I can make these two have the same base so that maybe I could combine them and use that exponent rule? Forrest, what's your idea? What is 4? What is philosophical? What is 4, if that's even a word? But 2 to the power of 2. And look, guys, we're back in grade 9 now. 2 to the power of 2 times 2 to the power of x. 2 to the power of x plus 2. Yeah, of course they're the same graph. We just use our power rules to show. And that's another strategy you guys could use. Try rewriting all the numbers in terms of the same base. All right, I have one last thing to show you guys. It kind of piggybacks on what we're doing next. You guys remember, let's go way back here. Let's go way back. If I took y equals x squared, and it's the basic parabola, looks like this. What did the graph look like when we did x plus 2 squared? When you added a 2 on? What effect did that have on the graph? Not wider. Skinnier? Not skinnier either. Where would the vertex be?
Lower.
Nope.
Higher. Right. Left.
Finally, it moves the vertex left 2 units. That's great. Yeah, right? Grade 10 stuff. Moves it left 2 units. Guys, check this out. I'm going to graph this guy and 2 to the power of x on the same grid. I can hardly contain my excitement. I just love sharing this stuff with you guys. So here is the graph of 2 to the power of x. Observe it in all its glory. Check this out. When you graph 2 to the power of x plus 2, guys, look at this. Every point has just been picked up and shifted over left 2 units. This point moved left 2 units. The point 2, 4 moved left 2 units. The point 0, 1 moved left 2 units. Guys, the same rules for parabolas and transformations work with our exponential functions too. Very cool. All right, yes, Sullivan. You have a question? Okay, I'll come around in a second, okay? All right, to wrap up this part, can you guys graph 2 to the power of 2x? And I'd like you guys actually to predict piggybacking on our conversation about transformations, think about what happens with parabolas when you add a number on the end. Think about what happened with the sine function or cosine function when you added a 1 on the end. After you sketch this function, predict what the graph of g of x will look like, and then we'll wrap things up. Yes? There was one in the practice from yesterday, actually. Yep. May I wear a pencil? So in this case, 1 over 3 means it's going to be decreasing, which you have. So you can think of it two ways. You can think of it as multiplying by a third. But another way to think about multiplying by a third.
That's my line. He's also
Okay, so the rule is you've got the y-intercept, and then you just are going to divide the values by 3. Yeah, perfect. All right, here I come. So the left-hand function, you guys should be very quick at graphing these now. Start at 2, doubles every unit. I'll even add -2, 0.5 there. All right. Possibly somebody who hasn't helped out yet today, a lot of you guys have, can you share your prediction of what this graph will look like when it's the same exponential function plus 1? Anyone have any ideas? Andrew, what do you think?
the left one.
Left 1. Not left 1. Although I had to think, because that sometimes is possible with exponential functions. We are close. Left 1 would be if the plus 1 was on the exponent, it would do that for sure. This one's on the very, very end. Forrest? Up 1. Just like with last unit, when you took sine x and you added 1 on the very end, it moved the axis up 1. The graph of this function is all these points moved up 1. But guys, so this is important. Not only are the points moved up 1, normally, for every single graph you guys have done so far, your function has had an asymptote, a horizontal asymptote at y equals 0. This one will not have its asymptote at y equals 0 because everything gets moved up by 1 unit. Can you guys pretty please draw a dashed line here? Our asymptote is moved up 2. I'm going to write it in a short form. We have a horizontal asymptote at y equals 1. It got moved up 2. All the points got moved up. So can you guys take all the points you had and just move them up by 1? So we were at 4. 1, 4 goes to 1, 5. 2, 8 goes to 2, 9. -1, 1. Everything just shifted up 1 unit. The idea here is that in real life, not all things will settle at y equals 0. Can you guys just humor me and pretend you're me with your coffee, you leave your coffee out or a hot drink or whatever.